Hey everybody, Mr. Clausen here. Just wanted to go over our unit on free body diagrams and frictions with you. The test is coming up soon, so hopefully this little overview will help us out. So where I wanted to start here is back at the beginning of the unit for us, which is how to solve problems using free body diagrams. The first thing you want to take a look at are the steps to solve any free body diagram. Remember, you want to draw the free body diagram. Then the important thing we're going to do this time is we're going to break any angled forces into their components. And so in the example problem we had over here, we have the guy pulling the sled at an angle of 30 degrees, and you can see we broke that up into tension in the x direction and tension in the y direction. Now in order to solve for that, what we would have to do is use trigonometry, SOHCAHTOA, to help us do that, but we've gone through that before. Now, the problem that people often want to skip is redrawing that force diagram, and that's been told to be super important, and we've done that right here, is drawing with just the component forces. Doing that, it makes your life a lot simpler. All right, so then what we got going on is we can start to create our force statements, and they're simply just a way for us to help figure out what's equal to what. So in this first one here, we're talking about what's going on in the x direction, and you can see the only two forces we have there are the force of tension in the x and the force of friction over here on the other side. And so since those are in opposite directions, we're going to subtract them out. The next one we had was the sum of the forces in the y direction, and so now what you're going to take a look is what's going on over there. So we got gravity acting down, but we've also got the normal force and the force of tension pulling up a little bit, because if we go back up here in the problem, you can see the guy is not just pulling forward, he's also lifting up a little bit. And so what happens there is the normal force isn't going to be the same size as the force of gravity like it has been in the past. It's going to be a little bit less because the guy is actually lifting up some of the weight there with it. So when you're done with that, what you have to do is you have to just make sure you're only adding the horizontals to the horizontals and comparing the verticals with the verticals. We did some mathematics here for how to do it, and you can take a look. Here's another way to think of it to visualize what's going on. All right, we did another tension problem in class, and so here's an example where something was being pulled down. So here's our mass right here. Something is being pulled down by the force of gravity, and then we have two ropes that were holding it at different angles. So we measured the angles in the class, and then we were able to figure out what the tension would be in each rope from that. So we redrew our free body diagram, as you can see over here. We wrote our force statements, and we were able to solve the following problem. All right. Now, we then did another problem with Homer. If you want to take a look at that one, that's the one we did here. It's very similar to that sample problem I just showed you, but using the tension, we were able to figure out the weight. And the key thing here is to redraw that free body diagram where you include all the forces that are just at right angles to each other. We did some other examples, like this one here. Now, when we saw these, they're a little bit different because this block is sitting on an angle. And what a lot of students wanted to do or are tempted to do is they see these diagonal forces and they want to break those up into their components. And that's doable, but it ends up just being a lot more work. The easier way to do this is to actually just take and change the way you're looking at the problem. So rather than looking at the problem like this, what you want to do is just take that problem and flip it so now it becomes horizontal. What we can see there is now instead of having two forces that are angled, we only have the force of gravity that is at an angle. The other key trick then is when you do this, gravity is going to be broken up into the force of gravity. We would call that perpendicular to the surface, and then also the force of gravity, and we would call this parallel. And so now you can take a look and compare the force of gravity parallel to the force of friction, or you could take the force of gravity perpendicular and compare that to the normal force because they're at the same angles. One little trick is where does this angle represent in the problem? But if you do it like this, where you draw your lines opposite of the normal force, this angle right here is the same as the angle of the incline. And so we did this as a learning check in class, and so if you go down, you can see we then did that work there with it. I redrew the free body diagram right here for us. And once again, this shows us that the force of gravity perpendicular, remember that's this one right here, is going to be compared to the normal force, and the force of gravity parallel to the surface is going to be compared to the force of friction. In this one, they all ended up being balanced because it was dealing with a block that was at rest. And if the block is at rest, that means that the block is in equilibrium, or the net force is equal to 0. Now, it's not always that way. In fact, we did a problem dealing with my daughter going down an ice slide, which I'm just trying to identify. There it is, which was this one right here. So my daughter slowed at a rate when she got to the bottom of a slide. And so here's an example where our force statement didn't always end up being equal to 0. So she actually did experience a net force. Now in the first part, her net force vertically was equal to 0 because she's not going up or down. When she got to the bottom, she was just slowing down in the horizontal direction. So there it was there. It was the sum of the forces was equal to 0. However, when we look at her horizontally, she did have an acceleration. And because she had an acceleration, this means she has a net force. Now, the important thing to do is when you figure out the net force, there's still people that want to think, or the common mistake that happens is, whenever somebody sees the acceleration, they want to put 9.8 in there, and that is not the case. In this case, the acceleration my daughter was experiencing is the 3.4 like it was stated in the problem. So the net force she would be experiencing would be her mass multiplied by the acceleration she was experiencing, giving her a net force in the horizontal direction of 68 newtons. Now, how do we use this to figure out the force of friction? Well, you can come down here to your force statement. The force, the sum of the forces in the x direction is going to be equal to mass times acceleration. And because my daughter was experiencing an acceleration, we would include that in there. And then the only other force we have in the horizontal direction is the force of friction. So the net force acting on my daughter, which was 68 newtons, is going to be equal to the force of friction in this problem. And now, like I said, I just wanted to show this one again because sometimes our net force is 0, and all the forces balance out like they have there for the normal force and the force of gravity. Other times, though, if the object is accelerating and experiencing some sort of acceleration, it's not in equilibrium, you will have a net force, in which case the net force needs to be accounted for in your force statement. All right, so we started talking about friction in this problem. Let's go through what that is. If I come up here, where'd all my notes go for what it is friction? Sorry about that, people. But here we are. We took these notes, looks like on the 29th, and we started talking about what is going to affect friction. So remember, friction is a force that opposes motion. It doesn't oppose necessarily the applied force. In fact, that was the example I wanted to do down here. It opposes the motion of the object, and it's always parallel to the two surfaces. So we had this example, say there's a runaway train and Superman is coming in to save the day. Superman is actually applying a force, in this case, in the same direction as the force of friction because we are trying to oppose the motion of the train. Now, where does friction come from? We've used the description so far that there's these little jagged teeth that are going on, that are interacting, that can cause it. And then, in fact, sometimes if things get smooth enough, what actually happens is there's interactions between the electrons of one atom in one material and the electrons in the other. All right. So that's a little bit about what can cause friction. Now, friction does come in different types. We have static or not moving friction, and then we have kinetic or moving friction. Now, kinetic can be broken down into subcategories of sliding, rolling, and fluid. Rolling and fluid are ones that we aren't going to focus too much on in this class other than realizing that they exist. We are going to be speaking most of our time and focusing on sliding friction when it comes to kinetic. Now, when we did this in lab, you guys dragged some stuff across the table, and often what we got is when you dragged across the table, you got this big spike and then followed by a little plateau, and then when you stopped pulling, it went down like this. And where this is trying to tell us is when this was happening right here, the object was at rest. And what you get is you get this big spike before the object starts to move. And what this big spike represents is that represents the amount of static friction acting on the object. Once the object started to get moving, which happened in this region right here, what that's going to correspond to is once the object is already moving, it's moving, so that's going to be the kinetic friction acting on an object. Now, there's a lot of reasons for why people think static is greater than kinetic. It has something to do with the amount of time that the electrons can make those bonds, or maybe it's the amount of time that the teeth fall in and interlock with each other, but it doesn't change the fact that this is what we see in laboratory, and that static friction is always going to be greater than the kinetic friction acting on an object. All right, how do we measure the amount of friction two surfaces are going to have? This brings up this word we talked about called the coefficient of friction. Remember, it is the Greek letter mu. It's a combination of the letter M and U. Different surfaces are going to experience different amounts of friction simply just based on how they are designed. We use the example in class of hardwood floors versus socks are going to be very slippery, so their coefficient of friction might be very small, say something like 0.1, whereas my socks versus the carpeting is going to be experiencing more friction and therefore have a larger coefficient of friction. Okay. Finally, what can affect the force of friction? We already addressed this just a little bit up there, one of which is the type of surface. So perhaps this one right here would be the hardwood floors versus my socks, and maybe this one is carpet. Okay, in lab, we found out that if you use a different type of surface, you're going to get a different amount of force of friction, because each one of these would have a different coefficient of friction value and a different amount of friction that's going to be there. The other thing you can do to change the amount of friction is you can change the force that's pushing those two surfaces together, which would be the normal force acting on the object. If you increase the amount of weight of the object or how much force is pushing those two surfaces together, what you're going to notice is if you increase the normal force, what happens is the friction also increases as well. And so what we were able to get in lab is when you found the slope of this line, we found that the slope of this line actually ends up being equal to the object's or to the surface's coefficient of friction. So we wrote it like this. Coefficient of friction is equal to the rise, or the force of friction, divided by the normal force. Now we often rearrange that into this little equation down here where we say force of friction is equal to mu times normal force, and it just helps us understand what are the two ways you can affect the amount of friction an object is going to feel. One is, this is the way we measure the type of surface, so we say surface type. Each surface type is going to have a different coefficient of friction, and so different surfaces, different amounts. The other way would be to increase its weight, or the normal force. There was a third way we were able to increase or change the amount of friction. So say you got a heavy object that you just don't want to be able to lift up, but you still need to move. If you wanted to push it to the side, so you're applying a force this way, and it's not quite moving, what you could do is you could fill those gaps with some sort of a lubricant, whether it be oil or wax. And what that would do is that would prevent these teeth from interlocking with each other, or the surfaces from touching and creating those bonds. And hopefully what this would do is it would reduce the friction. All right, so there's an overview of everything we've done this unit. If you have any other questions, please feel free to come talk to us sometime tomorrow. Good luck.